Hi everyone. We're going to study some passive design techniques that are specifically good for cooling. The two major passive cooling techniques are evaporative cooling and ventilation. But before we go on to talk about them, I want to mention that some of the techniques you've already taken a look at work well for cooling also. Solar shading, we talked about with day lighting in order to control glare, but they work really well as cooling techniques. All right. The envelope techniques keep heat in, but they also work well to keep heat out, and so they can be counted as cooling techniques. So in this video, let's focus on evaporative cooling, starting with what exactly is evaporation? Well, reach back to your grade school days and remember that evaporation is a phase change from liquid to gas. And we're specifically talking about water, so it's from water to water vapor. Now, in order to go from water to water vapor, there either needs to be a change in temperature or pressure. In our case, we're talking about temperature. So in the design field, we can take advantage of evaporation and the phase change because it requires energy. So water plus heat from the surrounding air is going to be water vapor. This means that when we add water, all right, we actually pull heat out of the surrounding air. And this is the whole basis for evaporative cooling. There's some advantages and disadvantages to evaporative cooling, all right? And the first advantage is major, all right? It uses far less energy than your active cooling systems, your air conditioning, all right? Also, the equipment is inexpensive and it doesn't use the same toxic chemicals. So where can you use evaporative cooling? Here in the US, it is used in the West. All right, you can see the map everywhere in purple is where evaporative cooling works very well. The yellow areas are kind of in between. It could work, could not work, depending on the system and your specific microclimate. And in the East, the climate is much more humid and evaporative cooling is typically not recommended. Around the world, take a look at this map. You can see everywhere in kind of the yellow are the dry climates. And then in the dark green, mid-green to dark green, is the humid climates where evaporative cooling won't work. So you can see that this is useful across a wide swath of the world. There's two major types of evaporative cooling, and then they can also be mixed, used together, and you can use them in conjunction with mechanical cooling, with air conditioning. But let's talk about these two basic types. The first one is direct. Direct evaporative cooling is when water evaporates within a building or in the fresh air intake. And so the air that's supplied to the space, your occupied space, is both cooled and humidified. All right, water is added to that air. It really only works in the most dry climates that we highlighted in the last slide. On the right-hand side of the slide, we have indirect evaporative cooling. This cools the building or the indoor air, all right, without humidifying it. And as such, it can be used and can be appropriate for slightly more humid climates than the direct systems. Let's take a closer look at direct evaporative cooling. By far the most common way to do this is with a swamp cooler. All right, and the basic mechanism goes like this. A fan is going to bring air in through a wet screen. And as the air goes through that wet screen, it is cooled and humidified, all right? And then the cool air is supplied to the occupied space. Looking at this diagram over here, we see the swamp cooler up here on the roof. Here is the fan. It is sucking hot, dry air in and supplying cool, humid air into the space. Right? You can see that this is a little water supply, a little sprayer. It is spraying water on this screen right here and keeping it wet. On the left over here, you see a little bit more complicated diagram of how a commercial swamp cooler might work. Go ahead and pause the video and make sure you understand this concept. So let's talk about indirect evaporative cooling next. And remember that this means that the occupied space is cooled, but not humidified. And the major traditional way, the main traditional way to use indirect evaporative cooling is with courtyards, fountains, and or pools. In a courtyard design, taking a look at this building section here, the courtyard is designed to shade your water feature, your fountain or a pool inside. The evaporation from that pool or fountain is going to cool the air. All right. And what you do is close off the windward side of your building and open up the leeward side. This will pull the cool air through your building, all right, while the water evaporation escapes out through the courtyard. Right? It's a fantastic way to cool your building. Finally, you can have indirect evaporative cooling devices. All right, take a look at the diagrams on the left. You can see that kind of in diagrammatic form, the direct evaporative cooling takes warm air, runs it through a water pad, right, and humidifies it, and the cool air runs off to the right. An indirect evaporative cooler is slightly more complicated. Again, we have warm air coming in through the left and cool air goes into the occupied space. All right, but we have a secondary airstream that will exhaust the humidity in another direction. It never goes into the occupied space. Here's what one of these evaporative coolers might look like. All right, in this case, the warm, dry air is coming in from the outside. All right, it comes through this indirect evaporative cooler, right, and it actually exhausts with the taking all the humidity with it out back into the outside. All right. On the other side, we have return air. This is already dry from the inside of your space, all right? But it's warm, it's warmed up. So return air is coming in through this direction. It goes through a heat exchanger in the indirect evaporative cooler, and then finally is cool and dry, returns to the indoor space. Thanks everyone. In this video, we've covered passive cooling techniques focusing on evaporative cooling.